Okay, good morning, everyone. Welcome to this session, Advancing Readiness for Deep Space Exploration, Status and Developments by the Alpha Magnetic Spectrometer Group. I am Dr. Jeremy Wood. I am a professor in the Space Studies program at American Military University, and I will be the chair of this session. If you have any questions for the presenters, please type them in the chat box and we will address them during the Q&A session at the end of the presentation. It is now my honor to introduce to you our presenters, Alessandro Bartoloni, Daniel C. Barrios, and Augusto Di Chico. Welcome.
Thanks again, Jeremy, for this introduction. And I just now shared some slides to introduce this panel. Of course, first of all, let me thank the organizer of this conference, Space Education Strategic Application, that give us this opportunity to present this panel. And what else? I think that I hope that it will be interesting for everyone. Most it will be about the something that is related to radiobiology of and the possibility to improve radiobiology in view of the deep space exploration. Let me see if yes, you should see the slide perfectly. So first of all, let me thank Daniel Barrios and Augusto Di Chico to join me in this panel. And the agenda is essentially a short presentation by myself about the MS, what is the alpha magnetic spectrometer on the DSS station experiment, and also why in the group we identify something that is, we think, be improved in view of the deep space exploration. And the two of these aspects are the Monte Carlo method codes for space radiation and shielding design that Augusto Di Chico will go deep in that. And the other one is the possibility to develop an ontology specific for radiobiology, for space radiobiology. We started this activity really recently in the group in Roma, but instead Daniel Barrios is involved in this kind of project since many, many years, and this is why she will give us some more insight on that. Let's introduce our speakers. Barrios is a medical doctor, PhD, with training and experience in data science. Since 2014, he has been participating in the development and deployment of the NASA GLAB database, and since 2022, he has been the deputy project manager of NASA's Life Sciences portal. Prior to that, his experience on NASA included projects involving science, data integration, semantic web technologies, spaceflight experiment operation, data system design. Daniel, thank you very much to be here today. And Augusto Di Chico is a nuclear engineer with PhD in the field of neutron and photon spectroscopy. His current research topics involve characterizing the secondary radiation field induced by high-energy heavy ions with materials level relevant to space exploration and analysis of double differential cross-section for secondary light ion production induced by neutrons and energy above 20 MeV. The secondary radiation is very, very important for deep space exploration because, of course, we have to travel in using starships. So it's not only about the exposition to the direct radiation, but also the secondary radiation produced by the interaction of this primary radiation with this kind of materials will be very crucial. So thanks also Augusto to be here. About me, I'm since many, many years involved in this, let me say, for what is my perception, spectacular experiment installed in 2011 on the space station. You can see the shuttle Endeavour that was, of course, the last but one space shuttle mission that gave us the possibility to install this detector on space. That is for this one here. The collaboration is very big. The Roma Sapienza group is just a little gear in a very, very big engine that is, of course, led by the MIT, and the spokesperson is Nobel laureate Sam Teams. But of course, we have the strong support from the NASA for all the operation part and from many other national space agency. You can see here the payload operation control room that is always active at CERN in Switzerland, where now Augusto is in the same place, I mean. And if you pass by the CERN, don't miss the opportunity to visit this operation control room. The main aim of the MS is to make study fundamental physics, to measure cosmic ray, to define something that is at the moment not clear or undefined, like dark matter presence, antimatter presence in our galaxy. But the main point for this panel today is the fact that to do that, MS is able to measure all the space radiation components that characterize in the heliosphere the cosmic ray of the charged particle present could be dangerous for the also deep space exploration. And it's a very complex environment because these different components interact and modify the exposition or the fluxes of the presence of the particle, not only with respect to the, let me say, spatial location, for example, if you are on the moon or around the moon on traveling to Mars, but also in time, because there is the interaction of different effects, depending from the radiation coming from the outside the heliosphere, the one produced inside the heliosphere, and also the one that is trapped in the Earth magnetic field, because if you want to go in the deep space, we have to fly through this part of the space that is called Van Allen belt, that is full of dangerous radiation. So the experiment by itself is a very characteristic of the one used at the accelerator to make high energy particle physics experiment and to improve this kind of knowledge is essentially a collection of more than one instrument. The simple basic concept that when a particle, that is the one that comes from the space, go through the experiment, live in each of the different instruments, you can see the acronym on the rows, a different signature. And so by analyzing the signal lived by each particle in this different detector, it's possible to reconstruct the different particles from the very light, as an example, electron, to very complex and maybe also potentially dangerous, like, for example, the iron protons or helium nuclei. So this is a typical measurement of the MS, in which you can see the absolute flux. That means we are able to measure how many particles per unit of time and unit of surface are going through the detector. But these are exactly the same that are going through any kind of object, biological matter, of any kind of matter that is exposed to the same radiation. From this graph that is on the x-axis, there are the energy, because of course the particles in space are a different energy. In that sense, it's kinetic energy, the speed of the particles. You can see that these blue ones are the protons, that the more diffuse, the more present in space. But you can see also that there is all the others particles present, from helium up to very heavy nuclei, also electrons, and so this is all the periodic table is present in space. Another opportunity that is very important for the radiobiology use of the data of the MS is the fact that the MS is continuously in operation. That means that since the very start, we are doing the measurement in time of the particle fluxes. So you can see here the color identify different particles. Blue are protons, red helium. But you can see also very important things. What I said before, I mentioned before, that the radiation fluxes is not constant, not only with respect to the location, but also it's not constant in time. So it's something that should be measured with great accuracy to understand the possible effect on the health of the astronaut. This is something that not a graph, it's something taken from a publication, just to let understand more in detail how much is accurate the measurement that this detector is able to do. These are referring more to many particles. This is just helium. And in this case, the color do not represent the different particles, but they represent the different components in energy of the helium. So for example, the red part will correspond to this energy range. The energy is measured in rigidity or gigavolt. And it means that is also important because from a radiobiological point of view, the danger is due to the fact that the particle, in going through the biological matter, release part of this energy. So the initial energy or kinetic energy of the particle is very important also to understand the possible danger. So the idea in our group is that 5 years ago, in collaboration with medical physicists from the Bologna University Hospital, we start to investigate the use of the MS data not only for fundamental physics open problem investigation, but for radiobiological investigation. This is also correspond in the same time at the fact that all these national space agencies are planning the return of the humans on the deep space. That means essentially the moon missions, Artemis program, and maybe in the future some missions towards Mars. With the respect, so we are combining these different things, that the fact that we have this detector in space able to measure with high precision the cosmic rays, the fact that the radiation has some radiobiological effect, so that means have some effect on the biological matter, and the fact that the human space exploration is restarted with great effort from any national space agency. The first thing that we did in the past was to try to define those effect relationship investigation. Those effect relationships essentially are something that try to correlate the radiation, those exposition, to the possible generation of biological effect. In this respect, we made some publications. This was a review that we published in 2021, in which we investigate the state of the art in this topic, and also we was able to identify all the possible organs that could be at risk or system that the body that could be at risk. And also we developed some tools using the R-script platform to produce this kind of dose effect model. And so we are now able to use the MS data to improve or to make study in the with respect. Recently, we start also two other kind of, let me say, paths of research. One was about, we started doing some radiobiological study that was related to the solar, specifically to the radiation generated by the sun, because this is something that could be very important for the beginning. And doing that, we start to develop an ontology of space radiobiology for literary review, and we keep in contact with Daniel Berrios and Jack Miller from NASA Ames. And so I will leave to them, to him, the fact to go deep in this kind of topic, because they are doing this kind of topic since many years. While another thing that we are now studying is try to understand how some codes, so-called Monte Carlo codes or Monte Carlo technique-based codes that are used to simulate the interaction of the matter, of the radiation with the matter, could be effectively used in emulate and simulate the space radiation. And this will be the topic of Augusto, that now I invite to share your screen and start with your presentation.
Good morning, everyone. I'm Dr. Augusto Di Chicco from the Physical and Technical Institute of the German Federation. In this short presentation, I would like to discuss with you one of my research topics, the application of Monte Carlo's codes to the study of material relevant for space exploration, in particular with the lunar regolith simulant. As you know, space exploration represents one of the biggest humanity challenges. With creating settlements on low Earth orbit or near Earth objects. But there are still a lot of scientific and technological problems related to three major health risks: microgravity, isolation, and radiation exposure. Each of these health factors may produce dangerous effect, and which may be also interconnected with each other. During the years, the space agencies have developed many scorecard of countermeasures, but we are going to focus more on radiation. The first question is, where does come from the radiation? In space, we have two main primary sources. The first one are solar particle events, which are sudden and sporadic explosion of charged particles, like electrons, protons, in particular helium, emitted from the sun. Really dense, but short-term. The second one is given by galactic cosmic radiation. It's the constant emission of charged particles from proton up to irons from the remnants of supernovae, which are really powerful explosions, but in deep space near our solar system, they are really low intensities, but ubiquitous, and modulated by the solar activity. Before to enter more deeply in the topic, I would like to introduce you the three most important concepts for nuclear physics or for nuclear engineering. The first one is the particle fluence. The particle fluence indicates how many particles pass through a specific surface. Keep in mind that not all the particles that are passing through this surface, they can pass with a different speed, and so energy. When it's passing through a material, for example, a human body, it can interact with its atoms, and the probability that such kind of interaction, which can be scattering, absorption, or fissions, is defined by the cross-section. This is the probability, and depends by the energy and the particle type and the target material. The final, if the particle is interacting with our body, for example, it may deposit a certain quantity of energy, and such quantity is called dose. But receiving those on my skin is different than receiving it on my lung or on my brain. We needed to quantify the harmness of radiation, and that's why we use the equivalent dose, which is weighting the absorbed dose as a function of the type of particle and the type of the biological tissue where we have received it. Why radiation is dangerous? Well, if radiation is entering our body, it may interact with our cell or even with the nucleus where our DNA is stored, breaking it. In the picture on the top on the right, you can see the effect of the radiation produced by gamma rays and by heavy ions. And as you can see, heavy iron ions, because of they are heavier, they can produce more ionization, more damage, more energy deposition. If the DNA is damaged during the reproduction phase of the cell, can happen. In the best case scenario, it can repair itself, or it can trigger its death. It can suicide. But in the worst case scenario, it can replicate abnormally, developing into a tumor. Higher is the intensity of the radiation, and more visible may be such kind of effect, like tissue burst, vomiting, hair loss, until death. So when the radiation starts to be dangerous, we need to identify two kinds of effects. The first one is the stochastic effects, which are below a certain threshold, 0.5 sievert, where we cannot see any direct effect, but long-term effect, like the development of cancer. While deterministic effects, they are visible, and the damage caused by radiation is certain. So we needed to protect ourselves, and let's take our planet as an example for strategy against radiation. There are two ways. The first one is active shielding produced by our magnetosphere. The Earth magnetic field is actively deflecting the high energy charged particle from the solar particle events of the GCR. But if the particle is passing through the magnetosphere, we have a second way of shielding, the passive shield, given by the Earth atmosphere, where the molecules contained in our atmosphere will interact with the charged particle coming from the sun, coming from the GCR, stopping them. And currently, this is the most used strategy. Try to think passive shielding like the concrete walls of a nuclear power plant or the walls of a spacecraft. In order to correctly design the shielding material for our spacecraft, we needed to understand how charged particle interacts with matter. The first one, they may interact, for example, with the electrons of the atoms of our target material through ionization. So the electrons are scattered out. Such kind of interaction is described by the Bethe block formula. Don't be scared by this long equation. The most important one is the ratio of the atomic number divided by the mass number. And in order to have an energy loss as high as possible, we needed to use lighter material, like the ones containing hydrogen. Aluminum is worse, even like heavier ones. Another way of interaction is that charged particles may interact with the nucleus of the target material through spallation or nuclear fragmentation process. During this case, the target atom is scattered is smaller fragments such as protons, neutrons, or lighter ions. And so basically behind the shielding that we are trying to protect ourselves, there is the production of a secondary radiation field, which may influence the equivalent absorbed dose. And also for this case, the most important parameter is the cross-section, which describe the probability of such kind of reaction to occur. Let's take a practical case. Therefore, let's imagine that you are an astronaut doing his spacewalks. As you can see on the bar chart on the left, for the case of free space, the biggest contributor to the equivalent dose are heavy ions, because the astronaut has no protection and the dose mostly come from heavy ions from the GCR. But if it is inside a spacecraft or inside a moon shelter, so is protected by a thick shielding, the biggest contribution comes from lighter ions like protons and light ions and neutrons, which may come from direct primary GCR because they are small enough to penetrate the shielding, contribute to the dose, or because they come from the secondary radiation field produced by heavier ions with the shielding material. So we need to predict such kind of secondary field for the shielding purposes. How can we predict it? We can do that thanks to the Monte Carlo method. The Monte Carlo method is a really powerful statistical technique used to simulate a complex physical process involving random interaction, such as the interaction with the matter, using always the material cross-section to determine the probability of such interaction. It's like a rolling a dice where each phase is differently weighted. Some phase will happen with more statistics, but also the other. So we need to launch many rolls in order to have a bigger accuracy. But what happens if we don't know the material cross-section? We need to rely on theoretical physical models that describe how the incident particle interact with the matter and giving an estimation of the material cross-section. However, because of the complexity of the interaction and the lack sometimes of real experimental data, physical models sometimes are inaccurate and discordant between them. On the two pictures on the left, you can see the dose reduction behind the shielding material, for the left polyethylene and on the left aluminum, as a function of the thicknesses. For the case of polyethylene, as you can see, these are the simulation obtained with the different Monte Carlo and deterministic codes, while the codes look like sufficient current because of the target material, in particular proton and carbon, they are quite simple. But in the case of the aluminum, well, higher and higher is the thickness, and the dose is not reduced, is even increasing. That's why, because there is this secondary radiation field produced by protons, neutrons, and electron particles, which is increasing the dose. And the other case is that there is a big discrepancies between the Monte Carlo codes, and we need to say which one is the most correct one, because we don't want to underestimate the dose reduction or to overestimate it. We need to do experiments. On the two pictures, in my field of research, I'm mostly focusing on these secondary neutrons produced by the interaction of high energy ions with space relevant material. Neutrons are particularly important because when the full GCR spectra interact with, for example, the aluminum, as you can see on the picture on the bottom on the right, the secondary neutron spectra is really broad and energetically broad and complex. And for the case, for example, of the moon regolith, neutrons have really an important contribution, even relevant for the case of absorbed or equivalent dose, for example, after 100 grams per centimeter square. However, there is a big problem. Actually, there are really few facilities able to accelerate high energy heavy ions relevant with the GCR. On the picture on the top on left, you can see the comparison of the GCR spectra for the different ions, proton, helium, oxygen, and iron. And the dashed line shows some institution, a particle accelerator facility, and these are the maximum energy which are able to reach. For heavy ions, for protons, of course, it can be higher. Such scarcity of facility means, and which of them they cannot create the full GCR, are just sometimes monoenergetic one. And as a consequence, there is a really big lack of experimental data, both physical and biological. Such a lack of physical experimental data means that there are so many nucleus cross-section, and so the major part of Monte Carlo codes need to rely on physical models, and there are also big uncertainties on the conversion coefficients needed to convert the neutron fluence into an radio protection operational quantity, the sievert, the equivalent dose. And finally, there is a big lack of data linking the physical with the biological one. The second question is how can we measure such high energy neutrons? At the PTB, we use sphere, which are basically big sphere of polyethylene and ones with an inner metal shell, where the neutrons, when it's entering inside the sphere, it will interact with the hydrogen containing it, constantly slowing down, reaching the central thermal neutron sensor and be detected. But the main problem with this system is that the initial information of the energy of the neutron entering inside the sphere is completely lost. What we obtain is just a number, a count rate. So that's why when we are performing measurements, we need to perform the measurements the same low position, but with a different sphere. If we increase the sphere size, we can see neutron having a higher energy, because neutrons higher energy will require more interaction in order to slow down and reach the thermal neutron sensor and being detected. For these the results I'm going to show you has been conducted in collaboration with the GSI founded by the ESA Core for the DIMOS project, performed at the Heidelberg Ions Accelerator Room. During this campaign, I had the possibility to measure, to use 3 ions at 430 MeV, protons, helium, and carbon. These energies are quite interesting because for ions and carbon, they may be found during the solar maximum activity, while for protons during that maximum of the GCR spectrum at the solar minimal activity. During this campaign, we used really nearby 1 meter of blocks of Moore regolith simulants, 9 boxes contain in PMMA. And if you're interested, you can see also the table showing the material composition of this Moore regolith simulant. So during this experimental campaign, I've placed our set of bone sphere at 4 emission angle, as you can see on the sketch, at between 0 up to 60 degrees, because in this way we can see the energy of the secondary neutrons at these scattering angles, because higher is the angle, smaller will be the energy, but I will going to show you later. So in order to have, as mentioned before, to have an estimation of the secondary neutron field found inside the experimental room of Heidelberg, I used 4 Monte Carlo codes: GM4, FITS, MCMP, and FLUCA. On the table, you can see, according to the Monte Carlo code and the ions, all the possible physical models, because it's only possible to use the sun at such high energy. Okay, perfect. So on this picture on the right, you can see the neutron energy distribution, the fluence of the neutrons as a function of the energy obtained with the 480 MeV helium beam with the Moore regolith at 0 degree. And these are all the simulated results obtained with all the Monte Carlo codes and the corresponding physical models. For our range of interest is the direct peak. So for neutron energy higher than 20 MeV, because such neutrons come from the direct nuclear fragmentation process or spallation process for protons for protons. Now the question is, which of, as you can see, there is really a big discrepancy between all the different Monte Carlo scores. During the simulation, I found some discrepancy which was ranging from the 20% up to the 60%. And we need to understand. My topic has two objectives. The first one is to characterize the real neutron energy distribution. And the second one is to say which of these Monte Carlo codes better reproduce the experimental one. In order to achieve this procedure, we needed to use the unfolding procedure, where we use our measured data. It's basically a code which basically, starting from our measurement data, it inverts the integral equation of Fredholm of the first order in order to obtain the experimental neutron energy distribution. But inverting such kind of equation, starting from 16 point, and we want to obtain a neutron energy distribution with 100, 200 energy beams, well, there is no unique solution. We need to help the unfolding procedure, which I used during this, for this case, Maxed code. We needed to help him by inserting a an a priori information, a first solution, which is the Monte Carlo simulation. By doing so, on this picture, you can see the comparison of the secondary neutron distribution obtained with the proton beam. The full lines show the initial, the dashed lines show the initial neutron energy distribution, so the simulated one, and the full lines show the corresponding result obtained with Maxed. As you can see, the two solutions, they are similar, but not coincident because of this high statistical uncertainty, because of the low number of experimental points. Just for showing you some few examples, here you can see the comparison of the results, the simulated spectra with the maxed one. This purple shadow show the set of solution obtained with all the initial Monte Carlo codes and their corresponding results. So there is no unique solution, but this shadow show where probably the solution lies. By comparing the different results with the initial Monte Carlo codes, for the case, this case is obtained with the carbon or with the Mon regolith, some models looks like to be better than the other. But for example, the quantum molecular dynamics for FITS and GM4, but for example, at 20 degrees, it's better the ones obtained with MCMP with the cascade excitation model. But as you can see, there isn't a coherence, there isn't a general Monte Carlo codes that is better compared to the other one. They are better maybe at specific angles. By applying the conversion coefficient from the neutron fluence to the ambient equivalent dose, we are obtaining this bar chart, which show the ambient equivalent dose, just two examples, at 0 degree and at 40 degree. The full lines show the initial simulated estimation, and the semi-transparent one, the results obtained with Maxed. The most interesting results is that all the results obtained with Maxed, they really show a small standard deviation of the order of 1–2%. On the direct peak, on the other hand, where we are most interested, they are really higher, but the standard deviation, you can see it is smaller. This table represents like let's say the ranking of all Monte Carlo code and their physical models. Generally, for protons and helium, it looks like that the NCL model reproduces better the neutron distribution at angle close to the bin, but not for broader one. While for the case of the carbon, FITS, QMD, GM4, BIC, and MCMP looks like better, but MCMP used in the cascade excitation model generally better reproduce the neutron energy distribution for the most of cases. So In conclusion, Monte Carlo scores are really simple and powerful tools that are of great help for modeling the radiation, its effects in space. However, to the surveillance, only relying on theoretical physical models for high energy particles, Monte Carlo scores show really big discrepancies. Even if some of these models can reproduce better this experimental data, the experimental data than other, no single code can accurately reproduce all possible experimental configuration. Maybe they are better only for that kind of material. So for the future, what is the fundamental? Well, it's fundamental to analyze and to have new material cross-section in order to cover the current gaps and improve the physical model implemented in the Monte Carlo scores. Testing a new shielding material and comparison with the simulated results to certify which of that given situation best reproduce the experimental one. And of course, what is more fundamental is the repetition of the experiments with different devices and by other institutions. Having only one experiment or one experimental data doesn't certify that this is the reality. We need more tests. In addition, communication and synergy among different institutes would contribute to the creating of new technological solutions. I hope that you enjoyed the presentation, and if you have a question, I'm at your disposal.
Thank you very much, Augusto, for this interesting and very nice presentation. I think that it's better to move all the questions at the end of the panel, even if now we will do a sort of swap to in a way different topics, but that may be also involve the main problem of this kind of investigation, that is regard the synergy, let me say the capability to take a lot of data, because there is a lot of data around, and have the ability to combine it to create some homogeneous data that is possible to, in a sense, improve the knowledge through combining different kinds of data. And in this case, also different type of simulation codes that will allow us to understand the interaction of the radiation with the matter. So please, Daniel, you can proceed with your presentation, and I asked Daniel, of course, to give us a basic introduction to ontology, because I think that this is something that could be very new for everyone.
Okay, can you see my slides?
Yes, perfect.
Okay.
Thank you.
Yes, there's a little bit of a shift, maybe a way into a little bit more of enabling technologies for these kinds of investigations. So I'm going to talk about ontology development to support data interoperability and open science in space, and in space exploration in particular. This goal in designing our data systems here at NASA is to support open science. Science can't be termed open unless its conduct is transparent. This involves both metadata transparency and data transparency. Metadata meaning we use concepts that convey what was done clearly and uniformly, and data transparency means using open standards for data whenever possible. Transparency enables scientific reproducibility, and really data cannot be understood and reproduced if the context in which it is generated is not completely understood. The problem with metadata, trying to achieve metadata transparency, is that currently there's just a lack of uniformity of metadata across data in various biomedical data systems at NASA and at other places. There's a failure to capture correspondences that are important, so-called linked data in experimental investigational data, such as this specimen was used in this experiment and it's the same as that sample from that experiment, those kinds of linkages. Extensively linking these kinds of objects in these experiments creates what's called a knowledge graph, and metadata harmonization and linked data development are key features of FAIR systems. The FAIR principles came out about 10 years ago now in open science, and both are evaluated in various, using various developing FAIR metric systems. So what is a knowledge graph? So a knowledge graph is a series of connected objects, each of which is completely and specifically identified and defined into a graph. And this is an example showing an experiment that has participants and utilizes hardware, and some of that hardware is an instance of a payload, maybe on a vehicle, which I don't actually have on this example graph, but that the experiment uses a facility and has certain programmatic information attached to it, funding and programs and identified and people. So what is a fair compliant knowledge graph? I kind of hinted at this, that the nodes in the graph, the links in the graph are drawn from these resources which are shared, these ontologies. We've seen a lot of acceleration in the last 10 years of development of these biomedical and other forms of ontologies too, that are enabling these knowledge graphs to be generated. An important component of that acceleration has been the development of the Obo Foundry, and I give the link there, which has now over 200 ontologies in various domain-specific areas that define concepts and their relations and axioms in various domains. We have put out the radiation biology ontology in 2021. We're working now on a space life sciences ontology. The first version came out in this year to specify, again, concepts to build knowledge graphs, and we've shared them on GitHub. So this is a little screenshot of what they look like shared through the bio. They're actually shared in an open framework, so isn't the only tool. Look at them. There are others out there, various other ontology viewing tools, but we do define things like many of the concepts which were just discussed by Augusto. Lots of various relationships and concepts around radiation dosing and effectiveness and such. So when you implement an ontology into these knowledge graphs, it winds up looking something like this, where every relationship and every concept, whether it's at the class level or the instance level, has an identifier associated with it, which you can pretty easily use to go look up information, annotation, contextual, hierarchical information on those concepts. And this leads to greater understanding and ease of sharing of data across experiments, across investigations, to synthesize results from multiple experiments into knowledge. So our goal is to build, as I said, these ontologies that we started out with, the radiation biology ontology, space life sciences ontology, as part of a larger set of open source ontologies that the community can use that would support other areas of science, earth sciences, astrophysics, heliophysics, and so on, and develop them in an open framework with using an open consortium. The radiobiology ontology uses an open consortium which anybody can join and contribute to, and its development is exposed on GitHub, so anybody can look at it and raise issues or new term requests, new relationship requests, whatever they want to see developed into the ontologies. And ultimately, these are being used right now to tag investigational data stored in NASA's Open Science Data Repository, which includes GeneLab, and Life Sciences Data Archive is starting to use these as well. So that's all I had. Alessandro?
Okay, yes, thank you very much. Sorry, I'm just waiting for the usual. Thanks for the attention. So no problem at all. So thank you. And so I think that I don't know if there is, Jeremy, if there is some question that we can take right now before to start the roundtable, or we can move on with the roundtable. Just up to you to make the decision.
Okay, we did have a few questions come in. I can read you those. I will scroll to them here in the chat. Let's see. Okay, the first question is for Augusto. He wants to Dr. Hala would like to tell you about using the GANT4 toolkit. Have you heard of a GANT4 toolkit?
GANT4 toolkit, yeah, is the main Monte Carlo code. So one, I think the Monte Carlo's code more spread actually in the world, basically. I think this is the ones with has the highest number of citation, maybe.
Okay. Yeah. Second question is also for Augusto. He wants to know, what do you think about this reference book? It is called Monte Carlo Calculations in Nuclear Medicine Applications in Diagnostic Imaging. And he has a link to it in the chat if you want to click on the link.
One moment, I'm going to check. In nuclear medicine, I never read these articles. 2013, it can be also a good article, but I think it will be a little bit more keep updated because such kind of field is advancing. Probably, yeah, it's always good to read a book, but yeah, that's, I never read it, so I cannot judge at all. I will read it.
The next question is also for Augusto from Dr. Hala. He wants to know if you use the Runge-Kutta method.
The Runge-Kutta. For the moment, I hear about that, but I cannot reply because I don't remember at all this method. Maybe it should be incorporated in Monte Carlo's code, but I don't want to reply if I'm not certain of something. So sorry, I will see. I will check.
Okay. The next one is not a question. It is just a comment to Daniel. It just says that NASA is making long-term commitment to building an inclusive open science community over the next decade. Open source science is a commitment to the open sharing of software, data, and knowledge, algorithms, papers, documents, ancillary information as early as possible in the scientific process. Good subject, Doctor.
Thanks for the compliment, I guess. I agree with that statement about the sharing, but I would also say it's sharing in a transparent and in a way that supports reproducibility of results, and that's the challenging aspects. I think probably even more challenging than just the sharing itself, but conveying all the contextual information to enable reproducibility and synthesis and reuse of data, building upon past experimentation. Thanks.
Okay, that's all the questions.
If there is still time for a question, I have a question for Daniel.
Yes, please, go ahead.
Daniel, so basically concerning your data sharing tool, are only, for example, American institute that can upload the data, or also other, for example, institute can do that if they are certified, for example, the data is good? How it will work?
So for the resources that we're building, the ontologies, we're doing it all on GitHub. So anybody can, any place that has access to GitHub can submit issues, can download products, review them. Our development lifecycle is, we look at issues that come in for new areas of modeling, build them into a draft version, release that out to the public, take more feedback, and build on it that way. So it's open to anybody to do that. We periodically take releases and build them into our data systems. And in terms of our data repositories, which are leveraging those ontologies when they do their data creation, adding metadata, adjusting metadata, whatever, for submitted data, those data repositories are generally they are variably open to accepting data from other non-US investigators. It just varies from repository to repository. The Open Science Data Repository at NASA, osdr.nasa.gov, is open to just about any submissions, but others are not as open and more limited to NASA-funded investigations.
Thank you very much. Thank you very much for the answer.
So I have a question that for Augusto that is linked to the one about the book. So you don't know the book, and this is because I think that on the Monte Carlo code simulation exists lots of books. But in your experience, because I think that you started 5 or 6 years ago to use the Monte Carlo codes, what you do recommend, apart a single book, but which is the after these years that you can recommend to a young person that want to approach the Monte Carlo code simulation, especially in the light that, as you mentioned in your presentation, this is not just using a mathematical model or technique, but just more mixed about the physics model and software that, in a sense, you cannot really modify, or you have to use as they are, as in a sort of black box modes. So what your suggestion and insight about that?
Yeah, you're completely right. Sometimes Monte Carlo scores, even at the open, maybe the open source one like a GM4, you can put a little bit your hand in the models, but for the others can be really more difficult. Well, to improve that, there are, for example, comparing always the experimental data with the simulated one, and making open source like clearly visible to the whole community, because there is only this way to helping the developers of the Monte Carlo codes, which are really deeply inside this course, to improve it and what is needed to be improved. Because it's really complex. They are really complex inside, and for just one developer, it's really a big task, in my opinion.
On the same topic, I would like to ask Daniel. Sorry, Daniel, if the question is not completely correlated to your work, but have you any idea if this kind of aspects are present in some ontologies? So that means that, as you mentioned, many of the aspects about radiobiology that was described by Augusto was a part of the ontology, the type of particle, if the experiments come from the use of protons, or if it was done in space, or if we regard genome or DNA or something else. So, but have you any idea about if this, let me say, aspect about simulation is also described in the ontology somewhere?
Yeah, actually, I was going to ask Augusto, or point out to Augusto, that while listening to his presentation, that I think there are certain concepts and relationships around shielding research and shielding design and shielding effects that we don't yet have in the radiation biology ontology. And so I would welcome you to put in an issue, or I could work with you to put in issues to get that basic definitional, annotational, and relationship descriptions for some of these concepts into the ontology as just part of our ongoing effort to improve it and build it out in certain areas.
I would improve it.
Yep.
Okay, thank you. So going back to the second question that is in the roundtable question, even if essentially we discussed this 1 month ago in NASA Ames, but can you say something about how, let me say, in developing comprehensive ontology for space radiobiology, this could be done, or what is still in place to do this kind of activity, to foster this kind of improvement with other research group? I mean, NASA Ames is, there is the division of biology and astrobiology in NASA. This is correct, I suppose, yeah. But of course, so that in a sense, it is the base of this kind of activity. But what is in place or could be put in place to enhance collaboration in that sense?
Yeah, so I think I understand your question, which is maybe how big a group is doing the kind of work that I'm describing. Not very big at NASA, unfortunately, but there are many other similar small groups at institutions all around the world that we connect with. Right now, we have an ongoing collaboration with Oxford and Cambridge on the radiation biology with ontology, with supporting their STOR database and the other radiation monitoring programs from Europe. So we meet with them regularly. We discuss their needs and our needs for this for the products we're building, the ontologies we're building, and prioritize work to get those into the ontologies to support those efforts. But anybody else that wants to join this consortium to develop these, we are open to accepting it. It's not it's just a GitHub consortium, so anybody can join that wants to and has a need to drive the development of these products, really not tied to any specific NASA divisions or programs, just as part of the open science community to get these delivered. Is that your question, Sandra?
Yes, please. I have another curiosity because any scientific community has some, let me say, event, conferences, something, group, or so. What is this kind of ontology or radiobiology ontology, but not only radiobiology ontology, main event or conference? If someone in the audience also is interested to understand how this community works, there is some main event in which it's possible to have, let me say, to present or to hear about that.
Yeah, so the Obo Foundry participates in the Consortium for Biological Ontology, ICBO conference every year, and there's a workshop coming up next week to look at an upper overarching ontology development, this Cobb product it's called. So I can maybe put some links in the chat for people to see a couple conferences that if they're interested in participating in this.
Okay, so please, I would like also invite Jeremy to if you want to say something or make a comment to Augusto and to Daniel, please.
Thank you. To Augusto, I've heard it proposed that water be put inside of the walls of the spaceship for shielding. Do you think that's a good idea?
It can be done, yeah, but the problem in space is like they are trying to. If I'm not wrong, the first shelter in the moon should be near like water sources in order to try to deflect it a bit. But that's yeah, it's possible. The water is one of the best shielding material against the radiation, so it's a possibility. For example, I was thinking to irradiate like block of ice, for example, to see the radiation shielding properties of against heavy ions, and to see also as well how secondary neutrons are produced.
Thank you.
I would like to add something that is in my mind since many times, and appreciate a lot the slides, Augusto, in which you mentioned the fact that on the Earth we are in a very optimal situation because we have the same time passive shielding and active shielding. I don't know, my idea is that sooner or later, if you want to really have let me say, an healthy life in space, we have to develop this kind of double approach in traveling, in lunar base, because I don't say in the near future, but if in the future we want to really stay for not only to go to the moon for a short time, but to stay permanently, I think that sooner or later water, aluminum, many other materials, but also active shielding should be developed and by by the let me say, the industries and the space agencies that is involved in that. And in this case, I think that the superconducting magnet are at the moment one of the most promising technologies to do that. I don't know what you think, but I think that from your slide, you have this also this approach in field.
I have some more questions that have come in if you want to hear them.
Yes, sure.
The first one is, I hope to see you in the next conference. The next conference suggested is the ICBO 2024 15th International Conference on Biology and Biomedical Ontology. And then I have the following question. Is a moon base still an end goal for moon exploration?
I don't know if someone want to take or I take it. I will start from Daniel because you know, no, okay. Okay, yes, I think that this is not something that, of course, made part of my everyday activity, but since I anyway involved in many, let me say, Moon Village activity, that is an association that I joined 2 years ago. It's a non-profit, completely different from the INFN or CERN. It is clear that the keywords of the next round of space exploration is to go to the moon to stay. In that sense, we really want to stay without it having a base. It's not possible. And in that sense, also, there is some let me say, not only dreams about that, but there is some activities that was commissioned from the space agency to some field. For example, if I don't go wrong, there is a project that is going on by Thales Alenia in, let me say, collaboration with the Italian Space Agency to implement what will be the first home for the first astronauts that will go to the moon with the Artemis mission. So this is something that I think is in the planning. There is two different approaches. The one is to have the gateway that is essentially a space station around the moon. But I think that also it is clear that even if in the first missions, the home of the astronaut will be the starship itself, sooner or later it will be something that is a moon base. I don't know if base is the right word in English to describe the first settlements that will be implemented on the moon. But with respect to what it was in place and planned, let me say 10 years ago or also 5 years ago, now the situation is completely changed. This is could be very easily also let me say, testified by the projects that are now going on by different space agencies, including the Italian one, but not only. I don't know if someone else would say something about that. No. Okay.
Says, thank you so much. I hope to contact you in the future, the next conference. And it's the same conference that I mentioned earlier.
Anyway, I just want to try to show the last slide, because maybe this could be of interest for the people that are, let me say, interested to understand what will be the future to stay on the moon permanently. There is, of course, a very important conference in Italy. And this is not in Italian one, is one of the most, any conference is important, let me say, but of course there is something which there is more people, and this is, for example, the AC that is organized by International Astronautical Congress. Last year was in Baku, 2 years ago it was in Paris. This year is in Milano, in Italy, in, let me say, in 1 month from now. I can say that the characteristic is that any kind of aspect of space exploration or space make part of the agenda of this conference. So in a sense, could be dispersive, but also if you are really curious not only about what is your direct involvement in research, but also what is around in the space, is a conference to attend. Of course, there will be talk about the MS radiobiology activities, but also not only. And more specific about the moon, since I also, let me say, with another hat, I'm joined 2 years ago in this non-profit organization that is named Moon Village, that is an international one. It's recognized in the Copos. And each year there will be a workshop and symposium. This year, it's 2 years ago was in Los Angeles, last year was in Tokyo, this year will be in Europe. It will be hosted by the Luxembourg Space Agency, and of course is mostly related to the moon, and in a sense, so it's also will be a place in which this kind of argument about the next what will happen in the future for the space exploration, and especially the moon space exploration, will be discussed. And I will like to thanks again the organizer to give us this opportunity. I would like to leave the last word to my colleague that was so kind to join this panel. So please, Augusto first, and then Daniel, if you want to add something.
Nothing really. Thank you to you and to the organizer for this fantastic opportunity, and I had the opportunity to meet you all. So I'm really happy. Thank you.
Yes, thank you, Alessandro, for inviting me, and I look forward to maybe future collaborations with everybody here, as I discussed before.
Thank you, Daniel. Thank you, Augusto. Thank you all.
Thank you.
Okay, so I guess we've come to the end here. We're actually a couple of minutes early. So hearing nothing else, I assume that we will go ahead and end right here. So that will give us a short break before the next session will begin, probably about the 12-minute break here. So thank you all.
Thank you. It was a nice continuation.
Thank
Thank
you.
you.